So firstly, I'd like to welcome everyone. This is the Women in Energy Australia Group's first webinar since we were created. So today our speaker will be giving a technical presentation, and then there'll be time for general questions and questions on the presentation at the end. I'm Maddie. I'm the current NGN B4 liaison and also the new NGN co-chair for 2021. And today we're fortunate enough to have Marina Delac from AEMO for today's presentation, which is on oscillatory stability in the NEM. So I thought we usually just give a brief overview of the CIGRE group to start off with. So CIGRE is the world's leading knowledge development and sharing program for power system expertise. It is a collaborative global community and has presence in over 100 countries, headquartered in Paris, France. The Women in Energy group is a subgroup established for all CIGRE members, providing networking and development opportunities for female CIGRE professionals and highlighting member achievements. So all of the information about the Women in Energy group and also the Next Generation Network, which you may have seen have usually host quite a few webinars throughout the year, is available on the NGN website. So you can express interest to get involved or to join the NGN or to find out more about CIGRE through the website. There's a join form where you can tick a box to find out more about the Women in Energy group. And obviously you can become more involved in CIGRE through becoming an active member of a working group or study committee where you can present your work and identify opportunities in your area of expertise. So if you want to find out any more information or get in contact with someone, you can just go to the NGN website and all that information should be there. So as well on our website, we try and promote all of our upcoming events, so any additional webinars or also webinars hosted by international CIGRE groups as well. So I know there was a roundtable discussion hosted by Italy, I think a month ago. So those events are all that information is on our website as well. So if you're keen to look at what's coming up, that should all be there as well. So as I said before, we're fortunate enough to have Marina from AEMO to talk to us today about oscillatory stability in the NEM. So AEMO is the Australian energy market operator. And Marina is a registered professional electrical engineer with extensive experience in power systems. Her career started more than 30 years ago in Croatia, and her early career focused on power system software development, load flow and dynamics, as well as software development for identification of instabilities. She has worked for Hydro Tasmania, Powerlink, Dixieland and AEMO with a focus on power system performance evaluation, modelling, generator compliance assessments and generator testing. So without further ado, Marina, if you want to take over and share your slides, we can get started.
Thank you, Maddie. Thank you. Can you just confirm that you see the screen?
I think I'm still sharing.
Okay. How about now?
Yeah, I think it's coming up.
Okay, excellent. Yeah. Okay. Thank you, Maddie. So as the title says, we'll talk about NEM oscillatory stability. And this presentation was prepared for engineers with no or very little exposure to oscillatory stability. Another thing to note that
hold on,
there
Marina. I don't think I can see the slides anymore. Are you able to try resharing? Sorry.
That's strange, because I can, it says that I'm sharing.
Yep, no, it's come up now.
Okay, please let me know. Please let me know if it disappears.
I will keep you updated. Thanks.
Okay,
Sorry
thank
to
you.
interrupt.
Not a problem at all. Also to note regarding terminology is that small signal stability, oscillatory stability, and rotor angle stability mean the same thing. And also, some of you may be much better experts, bigger experts than I am. So just to say that this presentation will focus on concepts rather than the very detail, such as how to tune stabilizing devices. Topics we'll cover is oscillatory stability in real life. What is oscillatory stability? How is it assessed? How is NEM kept stable, assuming that it's unstable without stabilizing devices? And what does future hold for NEM oscillatory stability? To set the scene, I just want to show you a video that goes around 2 minutes, a little bit over 2 minutes. If you don't hear the sound, that's okay, because I noticed in my last presentation, some people didn't hear the sound. That's okay. Sound is not important. Important is what you see. And also, yep, this will go for around 2 minutes. Maddie, can you just confirm that you see the video?
Yes, I see the video.
Yeah, thank you. Thank you. As you can see here, something that started as small due to wind ended up being quite big. And the event is not a power system event, but it could have been. I'm not entirely sure, but I wouldn't be surprised if oscillatory stabilities or instabilities appeared first in structures rather than power systems. And every dynamic system can suffer from oscillatory stabilities. structures, as we've just seen, power systems, electronics, biology, chemistry. And when I say dynamic system, I mean any system that can be presented by differential equations. Where in the big picture, oscillatory stability sits. So we have definition of power system stability by IEEE and CIGRE. And there are three types: rotor angle stability, frequency, and voltage stability. Oscillatory stability sits under rotor angle stability as well as transient stability. They are both short-term phenomena, whereas frequency stability and voltage stability, they can be long or short, depending on what's happening. Definition of oscillatory stability is the ability of the power system to remain in synchronism when subjected to small disturbances, such as small voltage steps, not faults. Faults would be transient stability. Then tap changes, small load changes, and non-significant line switchings. Why is NEM susceptible to oscillatory stability? One of the reasons is that the mainland NEM is not interconnected enough. And if in a few moments we'll compare NEM design with the European network design and see the difference. More interconnectors, more meshing, lower impedances would lead to better stability overall, not just oscillatory stability. So here we have a long, not meshed enough system. If you look at Tasmania, you may not think that Tasmania has the same issues, but it does. It's actually, without stabilizing devices, it's unstable as well from small signal point of view. And that is, it looks like a mini NEM. If you have a look, there is a long network that is not connected here on the West Coast. And this system suffers from oscillatory stability issues in the same way as the mainland NEM, and it cannot operate without stabilizing devices. Now have a look at the European system. It is very meshed, well interconnected. However, on the fringes, there are interconnectors, and definitely they have stabilizing devices as well. So the system may be not that prone to oscillatory instability, but still stabilizing devices are needed in some areas. Now, NEM is very similar to Chile. Chile is 3,500 kilometer long network and suffers from very similar issues as the NEM. Now, why does this happen? I introduced long networks, so that is one thing. But another thing that happened that younger engineers may not be aware of is that all synchronous generators designs had excitation derived from main and pilot exciters and rotating exciters. And there are still power stations with generators in the NEM and Tasmania that are of that design, such as Korea, Gladstone, and there is a number of them in Tasmania. Such systems are very slow to respond, let's say, to faults. So if there is a fault, voltage support is very slow to build up. So in synchronous generator jargon, what we say is that synchronizing torques were low, but damping torques were high. So such system didn't suffer much from oscillatory stability. So what happened some decades ago was the introduction of static excitation. And what that means is that excitation is derived from generated terminals via excitation transformer and thyristors. And such arrangement is great for large disturbances, because when there is a fault, such generator would respond in a fast and forceful way. So what we say is that synchronizing torques are much higher for static excitation system than for, let's say, rotating in excited systems. Now, such an arrangement reduced damping torques. And why is that? Because static excitation with its fast response have relatively high AVR gains. And high gains are really great for voltage recovery. But these high gains reduce the damping torques. And some of you that have been involved in the AVR tuning, you would know that AVR gains have to be limited. You cannot go with the gain high forever. They have to be limited, and something like 500 per unit is a good advice. And this was also the reason why stabilizing devices were introduced, because power system stabilizer injects extra damping torque. So at the same time, a generator can have high synchronizing torque, which is a win-win situation. But that means that you have to have stabilizing device. So when you combine deterioration of damping torques with the long network, high impedances of the long network and high impedances facilitate weakly damped inter-area modes, and I'll talk about those in a second. Power system stabilizing devices are absolutely essential in such systems. Now, when I talk about power system stabilizing devices, some of you may have heard about power system stabilizers, and they are installed on synchronous generators as part of excitation. But they can also be installed on FACTS devices, STATCOMs, SVCs, and then they are usually called PODs, power oscillation dampers. So what is the workflow? How do we analyze the power system, such as the NEM, to find out what sort of stability we are dealing with here? So you have to have two types of software. So one is time domain software, such as PSSE, say, that would provide you with the load flow. And then you have to have small signal stability software, such as MATPAC, developed by University of Adelaide, and ASSAT, developed by PowerTech in US. And this software, small signal software, will read your load flow with a particular scenario you want to study. Small signal software also needs one more input, and that is a dynamic model of all your control systems. And unfortunately, these small signal models are developed for a particular software. So you cannot have one universal small signal model that all software packages will read. You have to develop this specifically for particular software. Input for MATPAC is different from input to ASSAT, for example. So once you have your load flow or a scenario you want to study, or many load flows, which is usually the case, sometimes thousands of load flows, and you have your small signal models, you can calculate eigenvalues, eigenvectors, and participation factors, and I'll talk in more details about those. Now let's have a look how oscillatory stability is assessed. And concepts that are important will be covered from now on. So software such as PSSE will model nonlinear systems with algebraic and differential equations. So algebraic equations are not differential equations, and differential equations are differential equations. I think all engineers would be aware of those. So let's say load flow is represented by algebraic equations and dynamics by differential equations. And to be able to analyze oscillatory stability, such non-linear dynamic system has to be linearized. And as I said previously, software such as MATPAC and SSAT would do this linearizing for you. Once you have this linearized system ready, it is represented by state matrix, which is linearized differential equations, various states, which are, let's say for synchronous generators, this is various angles, speed, fluxes, and so on. There are many of them. Eigenvalues, and they are also called modes, right and left eigenvectors, and they are also called mode shapes. Once you have these 4 items, you know a lot about your dynamic system. And by the way, for those of you that are familiar with control systems, states are related to integrators in your control systems. Not just control systems, it could be any system, such as alternator would also have integrators. So if you have 100 integrators in your dynamic system, that means you'll have 100 states, 100 eigenvalues, 100 left eigenvectors, and 100 right eigenvectors. In the NEM, we have thousands of those. Not of them, fortunately, are important, but there are many, many states in the NEM. And hopefully the rest of presentation will emphasize what is important. So eigenvalues will show you whether the system is stable for small disturbances. Right eigenvectors will show you who participates in certain modes. And I know the meaning of mode is not as clear as yet, but I'll talk about it more soon. And this is an issue of observability. So if you see who is participating in certain mode, you're observing that mode. Left eigenvector, it tells you how much participation is available in certain mode, and we call that controllability. Because if you find out that certain generator participate in certain mode, well, perhaps you can control that mode via that generator. And that is called controllability. Now, we have this right and left eigenvector. Wouldn't it be nice if there is one entity that combines the 2? So, shows you who participates and how much. And that is participation factors. Participation factor is a result of multiplication of right and left eigenvector. And it shows you how much certain state participate in certain eigenvalue. And if you know that, you will know where is a good place for your stabilizing device, and hopefully some example that I'll show you will illustrate exactly that. Okay, let's I want to introduce the concept of eigenvalue. Once dynamic system has been linearized around operating points of your load flow, we can calculate eigenvalues. So what we are seeing here is the x-axis that represents damping, expressed in meters per second, and the y-axis expressed in hertz or radians per second. Now, NEPA per second, NEPA has a similar logarithmic definition as decibel. It's only that NEPA uses the base of natural number E, 2.7, while decibel uses a base of 10 algorithms. So they are quite similar. And sigma is the real part of the eigenvalue and has to be negative for dynamic system to be stable, whereas j omega is imaginary part of the eigenvalue and represents frequency. Usually we represent in radians per second, but it can be hertz. One thing to note that sigma and frequency could be zero. So let's see what different eigenvalues mean for time domain. So let's say your eigenvalue is sitting here. So it has negative sigma and it has certain frequency. So that means that you will have certain frequency in your response, but it will be very nicely damped because your sigma is negative. If you look at this point here, frequency is zero. So how would that look? There is no frequency attached to it, and there is nice exponential decay. This sigma is even bigger in the negative sense, so it means exponential decay will be even faster. Let's look at this region. So you have positive sigma, you have certain frequency here, so what happens here is unstable response. So you definitely don't want to be in this region. What about this one? Frequency is zero, will you have exponential growth, a little bit like COVID. What about here? Sigma is bigger, so you will have even stronger exponential growth. And finally, there is the point here. So sigma is zero, but it has certain frequency, so you will be marginally stable. But any small disturbance to such system may throw it into instability. So your linearized system definitely shouldn't be wherever there are red crosses. You always want to be in this region, otherwise you'll have instability issues. Another way to show, just to illustrate, so in this region, you are nice and stable. In this region, you are not nice and you are unstable. Another term I want to introduce is damping ratio. Just so that you are aware, because damping ratio is defined in National Electricity Rules, Chapter 10. And damping ratio combines both sigma, damping, and the frequency of a certain mode or eigenvalue. Having time of 5 seconds is still used for frequency between 0.05 and 0.6 hertz. So halving time is the time needed for the amplitude to halve. And some people will know that before damping ratio requirement, early version of the rules required the response halving time being 5 seconds or less for all frequency. And next slide will show why having time for all frequencies in the early version of the rules was replaced by damping ratio for some frequency. And here is the reason. If you look at these two responses, what you see is that they both have 5-second halving time. So in 5 seconds, both of these responses get to half of the amplitude. But we don't want, but the first signal will halve after 2 cycles, and the second signal will halve after 10 cycles, and that is clearly a problem. We don't want that many oscillations in a power or voltage response, as these oscillations may cause further issues, such as interactions with other dynamic systems and that could make situation worse. So damping ratio avoids this, as it takes both frequency and damping into account. So that's why halving time for most frequencies has been abandoned. Now, putting all this together, it's a lot in this slide, but let me emphasize what is important. So what we did here, we applied this Chapter 10 rules requirement to this damping x-axis and frequency y-axis plot. So what we said here, for this frequency, we want 0.4 damping ratio. Here we want 5-second halving time, and here we want 0.1 damping ratio. So your linear system is, you want it to be here. Although zero damping is here, you may say, well, why don't I want to sit in this area here? Well, it's better to be further away as possible from the zero line, and this is some sort of a security that was introduced. So you definitely don't want to be in the area that's reddish here. You want to be in this white area with your linearized systems. Systems with more inertia will have its eigenvalues in the lower frequency regions here, and the opposite is true for low inertia systems. So let's say in Tasmania, modes will be sitting in higher frequency area, whereas in the NEM they may be sitting here in the lower frequency area. So governor modes have the lowest frequency, then there come exciter modes, inter-area modes, and they are the least damped modes in any power system, not just NEM, in any power system. So these modes here are very, very important. Then you have local intrastation modes and control modes, and I'll talk about this in more detail soon. And there are torsional modes here on the top, but just to mention that the scale is not linear here for these subsynchronous torsional modes. It doesn't mean that torsional modes appear around 12 radians per second. They appear at much higher frequencies. And torsional modes are modes of turbines. And if you have unstable torsional modes, that can actually break your turbines apart, and you definitely don't want to excite these modes. The danger of these resonances is with the cylindrical two-pole generators and interactions with shunt capacitors, for example. So whenever you are installing shunt capacitor in your system, or series capacitor, or any FACTS device, you want to check that you are not exciting torsional modes. Hydro generators' torsional frequencies are much higher and usually are not an issue. Okay, so far we've covered eigenvalues. So next step is to introduce eigenvectors. To do that, we have to introduce the concept of linear transformation. And I mentioned that previously. If you have non-linear representation of a power system, you linearize it and you get linear transformation. But what does that actually mean? So linear transformation is something that constantly happens in the power system steady state. So small load changes and tap changes are example. So let's visualize that in another way. Let's apply linear transformation to Mona Lisa. We draw two vectors here. So we have red vector and we have blue vector. Then we do a linear transformation. So we slightly adjust Mona Lisa's painting. So we have applied small disturbance, small change via this linear transformation. What has happened to these two vectors? If you look at them, red vector is still pointing just right to the nose, and blue vector is still pointing to the shoulder. But red vector changed its angle, but blue vector didn't. And this vector that didn't change the angle is called the eigenvector. Just note that this vector's amplitude may change, but the angle cannot, to be eigenvector. And that tells us something. If the system changes, such as with these small linear transformations, there are some entities in our dynamic systems that will stay the same. So we could use such entities to improve the responses of the system, and such as this eigenvector. We can use that for certain purpose. So if we ask ourselves a question, is red an eigenvector? No, it's not. It changed the angle with linear transformation. Is blue an eigenvector? Yes, it is, because it didn't change the angle. It may change amplitude, and I will introduce that in the next example. So hopefully this will help to visualize the concept of eigenvector. Another example is present another example. It's called Bob's linear transformation, and it's a very broad analogy that mathematicians among you may question. But as I say, it's a broad analogy to give you an idea of interplay of eigenvectors and eigenvectors, eigenvalues, and you'll see where I'm going with this. So say we analyze a person with a big ego. This person, let's call him Bob, will have a dominant eigenvector that is ego. Why is that an eigenvector? Because no matter what linear transformation you do, no matter what happens to that person, Bob, this eigenvector will still point in the same direction, big ego. So it is a dominant eigenvector. So it's a good place to start a study. So Bob's current ego eigenvector is this. Another person that we'll call Alice is giving Bob lots of compliments, and that's linear transformation. It's changing the system slightly. So what will that do to Bob's ego eigenvector? So ego eigenvector will increase due to flattery. And this amount of change we call eigenvalue. So eigenvalue here is 2 because eigenvector increased by 2. So that is the concept of eigenvalue applied to eigenvector. So we see here final ego eigenvector is 2 times larger than Bob's original ego eigenvector. So the value of the eigenvalue here is 2. In the case of Mona Lisa, eigenvalue was 1 because the amplitude of Mona Lisa's eigenvector didn't change. But here, eigenvector changed, and eigenvalue attached to this eigenvector is 2. Now let's consider that instead of seeing Alice and getting lots of compliments, Bob visited Dalai Lama. And Dalai Lama's impact via his linear transformation, which is how he worked with Bob, is such that Bob's ego eigenvector decreased. And again, the number that reduced the eigenvector ego is called an eigenvalue. So in this example, what we have Bob's original eigenvector, which is this value. He visited Dalai Lama, ego eigenvector reduced, and the amount by it reduced is called eigenvalue, which in this case, it's 0.5. So this is a broad analogy just to get you an idea what eigenvalues do to eigenvectors. And just to mention here, I mean, Bob could have, and probably has, other eigenvectors that are consistent through his life. For example, all his life, he may have liked blue color. So that's his eigenvector. Or he likes certain types of movies. That's another eigenvector which doesn't change with transformation or time, say. But there are some eigenvectors that are dominant eigenvectors in power system analysis that we like to study. So not all eigenvectors, but dominant eigenvectors. So let's introduce the concept of modes. I've been talking about modes. So what is a mode? So we have a system of 50 Hertz frequency, and then there is a mode that we would call 0.3 Hertz, or we also call it QNI or I20 mode. By the way, 0.3 Hertz is very close to 2 radians per second, and that's why this 20 states here. It's I 2 radians per second. So when we analyze in small signal software, we analyze our system, one of the results will be a mode of 0.3 Hertz or 2 radians per second. Now, how does that relate to this 50 Hertz frequency? So what happens here is that this 50 Hertz is modulated with 0.3 Hertz. So in a way, mode is a frequency of a frequency. So when I say that the QNI mode, for example, has the frequency of around 0.3 Hertz, that only means that 0.3 Hertz modulates 50 Hertz signal. And we don't have to study 50 Hertz because we assume it to be steady. So the only thing we study in small signal software is this modulation. So hopefully that explains the mode, because I know that I was confused many years ago. What are these small frequency related to? How do they relate to 50 Hertz? So for those of you who wondered, that's what it is. Okay, so we are still with eigenvectors, and hopefully previous analogies will help you understand power system eigenvectors. In the NEM, there are several thousand eigenvectors and eigenvalues, but most of them are not relevant as they are well damped and don't pose any issues. So that means they have, when I say well damped, they are all located in negative sigma region. Important eigenvectors are those that are related to weakly damped eigenvalues or modes. So you can use the term eigenvalue, you can say mode. We call such modes dominant modes. So let's analyze eigenvectors on the example of the so-called QNI mode. And QNI stands for Queensland New South Wales Interconnector. So for all those young engineers, Queensland was connected to New South Wales network only in 2000, and that is when the QNI was commissioned. Once the circuit breaker was closed, the new mode was created that didn't exist before. The mode was called QNI or I20, 20 referring to 2.0 radians per second, which is frequency of that mode. And As a note, at that time, only Gladstone generators had stabilizing devices damping the QNI mode. Without these devices, NEM would be unstable. Blackwell and Greenback, as we see with their stabilizing devices, followed in the years after. So what do we see here? So this graph shows right eigenvectors related to synchronous generators. There are no SVCs shown here. SVCs will be introduced in the next slide. Right eigenvectors are related to the observability of a certain eigenvalue. So for this 1.95 or close to 2 radians per second mode, we see that oscillations related to these modes will be observed on Queensland generators and many South Australian generators. You have to look at the length of these eigenvectors as well. So let's say at the moment we neglect Victorian generators that are somewhere in the middle and New South Wales. So what we see here is who is oscillating against who. So Queensland generators are oscillating against mostly SA, but a little bit New South Wales and Vic generators. So this is dynamics going on in QNI with QNI mode. And this mode doesn't change much in this sense. There is always Queensland oscillating mostly against South Australia. And when I say Queensland, it doesn't have to do anything with the state or region. It's just NEM is very tidy in the sense that states are connected via interconnectors. And we can say Queensland oscillates against SA because Queensland is on the other side of the interconnector QNI. If network were designed differently, I wouldn't be able to say that, but I'll illustrate that very soon. So here, next slide, I want to show you participation factors. So we said that left eigenvector show you where is the best location to control a particular mode or eigenvalue. So if we multiply left and right eigenvector, we get participation factors. So for QNI, what we get is that the best location to damp this mode is 2 radians per second mode is at Greenbank, South Pine SVC, Blackwell SVC, Swanbank E. And on some of these devices, Swanbank E has power system stabilizer, Blackwell and Greenbank have power oscillation devices. You've seen in the right eigenvector that South Australia generators were prominent. But if you look at participation here, they are well down the list. So installing a stabilizing device at Pelican Point may help, but not as much if you have stabilizing device at Greenbank. So participation factors are really useful. Okay, so let me introduce the modes, NEM mainland modes. And they are, when we say modes, they are related to electromechanical modes that are not well damped. Electromechanical modes by its nature are not well damped. So, as I said, NEM has 4 main areas separated by interconnectors. And this topology is very tidy, so we can say Queensland oscillates against SA. Analogy for such topology could be springs, represented with masses, forces, friction, and spring constants. So you can visualize that if you apply a small disturbance to a spring, the whole system will start to oscillate, or swing at certain frequencies, such as Tacoma Bridge oscillations started by wind, for example. The theory says that if there are n generators, there will be n minus 1 or 3, in this case, inter-area modes. So there are four generators divided by interconnectors. So they tell us n minus 1 is 3, so we will have 3 inter-area modes on the mainland NEM. Mainland is connected via HVDC link, and electromechanical modes will not propagate to Tasmania and back. Tasmania has its own electromechanical modes. Now these 3 modes are called I20 or QNI, I25, so 2.5 radians per second, and I35, 3.5 radians per second. And by the way, radians, it's 2 pi f, so you can calculate frequency easily from that. So QNI mode has the lowest frequency, and it has the weakest damping. It's without stabilizing devices, it would be unstable. So inter-area modes, so we see are between 2 to 4 radians per second. In Tasmania, they are between 5 and 6 radians per second. So a little bit higher because Tasmania has lower inertia. So let's have a look at the nature of these electromechanical modes on the mainland NEM. So what we have here, we have I20 QNI, so Queensland generators oscillate against South Australian generators, I25, usually SA New South Wales against WiE, although this can change slightly, but most of the time this is what happens, and I35 mode SA and Queensland oscillate against New South Wales. There is another mode that you have to be aware of. This is local mode, where generator oscillates against the rest of the system. These modes are usually of higher frequency. And then there are intrastation modes. Various generators in the same plant oscillate against each other and against the system. So the next slide will show you when we do our small signal analysis without any stabilizing devices, what you will see is sigma is x-axis, frequency is y-axis. You will see that we have very many eigenvalues in the unstable region. So without stabilizing devices, the NEM is unstable. So we certainly don't want that. I mentioned Tasmania is very similar. It's also small signal stability unstable without stabilizing devices, and this is actual measurement at John Butters with commissioning of the first stabilizer. So this is without the stabilizer and just a small step in the voltage reference, and this is what happened. So very similar to the NEM. So how do we introduce damping? So we established that NEM and Tasmania power system are unstable without stabilizing devices. So how do we introduce this damping? Okay, let's look at the modes. So QNI mode is sitting here. For unstable case, just remember it's on the 0 frequency line, on 0 damping line, and let's see how we can correct that. So here we have I20 QNI mode. So we have generators, important generators swinging in Queensland against South Australian generators. And the one thing to mention is that these eigenvalues and eigenvectors will be different for various load flow scenarios, but the nature of them will stay the same. So most of the time you will get very similar eigenvector distribution as you have here. So to find out where is the best place to put place stabilizing devices, we multiply left and right eigenvectors. We get the best of the modes, observability and controllability, and this multiplied matrix is participation factors. And it seems, and that's the case, we know that the best place to stabilize QNI mode is to put power oscillation dampers on this SVC, and the major contributors to QNI damping are Greenbank and Blackwall SVCs, and that's where pods were installed. This is to illustrate the nature of I-25 mode. Again, one side of interconnectors oscillate against other. I-35 is a little bit messier because you have two regions on one side against two regions on the other side. Local mode here, or Torres Island, for example, where unit 3 oscillates against the rest of the system. And if you look at the frequency 9 radians per second, so it's much higher than 2 radians per second, but that's okay, that's local mode. Then there are intra-regional modes, just to be aware of. For example, here, Southern Queensland versus Central and Northern Queensland. This mode is well damped. If it weren't, we would look again into participation factors and find the best placement for stabilizing devices. Now I want to show you intrastation mode, and in this case, Torrens Island, or TIPS B, we call it, in South Australia. So what we have here, we have TIPS B2 oscillating against 3 and 4. One was out of service. So again, this intrastation mode is of higher frequency, but usually lower than the local mode. So when we put stabilizing devices as shown by participation factors on Greenbank and Blackwall SVCs, for QNI mode, which is the weakest damp mode in the NEM, our QNI mode moves to almost 0.5 nippers per second. So this is how you would manage the weakly damped modes. This weakly damped mode could be local mode or intrastation mode, where generators oscillate against NEM or in the plant against each other. Same, very similar analysis would be applied. So this is good result. Now the way stabilizers were tuned in the past were for the local mode and inter-area modes, but national electricity rules don't require that. So usually what happens when old AVRs, automatic voltage regulators, are replaced with the new digital devices, owners would tune their PSSs for the local mode only. So damping of inter-area modes is now left to power oscillation dampers. And as I said, QNI, the weakest damped mode, resides with Blackwall and green bank pods. Now, other devices such as batteries may be used for damping as well. But this area is still under investigation and research. So hopefully in the future we may use more generators, more types of generators for damping. One thing to emphasize is that when stabilizing devices were tuned, they were tuned for the network at the time of stabilizing device commissioning. So for the network and generation at that time. As network changes, a new generation is connected, these devices have to be assessed again continually to make sure they are still tuned effectively. Especially with the displacement of synchronous generators by asynchronous generation, that will change, and it has changed the nature, damping, and the frequency of the modes. So we definitely have to continually assess small signal stability to see that our stabilizing devices are still targeting the modes we want to target. So there is lots more to discuss here. As I mentioned, how are the modes changing with synchronous generators? Displacement. This is the big issue, especially in Australia. Are the PSSs and pods still optimally tuned for relevant modes? Do we need more stabilizing devices? How to tune stabilizing devices? How will network limits in the future be affected by the displacement of synchronous generators? Algorithms for measurements, for analysis of measurements data, that is a big issue as well. And the last one is mainly for AEMO, how to automate measurement data collection and analysis so that we can get quicker results when we want them. And this is my last slide. Maddie, this is it.
Oh, thank you very much, Marina. I did get one question. So for small signal studies, I guess is on the topic of how modes are changing with synchronous generator displacement. So small signal studies using machine RMS models focus on electromechanical stability of synchronous generation. Have AEMO or Adelaide Uni been developing linearization of the control systems associated with inverter connected generation to identify oscillatory interaction between those controls and synchronous machines? So,
yeah, yes, we are definitely in the process of that. But still, for the time being, asynchronous generation is modeled as a negative load. There are two schools of thought here, as far as I know, and that is that asynchronous generation has no impact whatsoever on electromechanical modes, and there is school of thought that says that's not correct. There is impact, and without studying our system, we won't know which one is correct. It's probably a mixed bag, I would think. At this point in time, in the NEM, oscillatory stability related to asynchronous generation is mostly related to higher frequencies. As some of you may know, there are pockets in the NEM that regularly oscillate at much higher frequencies. So it is small signal stability, but it's happening around 19, 17 Hertz. And that is something that we cannot model yet. with small signal software that we have and the models we have. So in my view, what we have to do, yes, we have to develop asynchronous generation, linearized models, and have a look for ourselves whether this displacement of synchronous generators, how it changes the modes.
Oh, thanks, Marina. And on that as well, I might just add a follow-up question. If we're developing models for IBR, do you think that there'd be a possibility of having like a generic linearized wind farm model that we could tune, or do you think that we'd have to get information from generators to, have them provide some sort of linearized model or have input to that, or do you think there's a possibility to develop generic models that we could tune?
I hope so. I hope there is
Yep.
possibility to do that. But before we decide, yes, that's the way to go, I think we would have to carefully look into this and see whether that is warranted, because control schemes with one OEM could be different from the other OEM, and having generic model for all of them may be not the right way to go. If we find out that control systems in asynchronous generation, they are all converging towards the same controls, then yes. But if they all differ, or groups of them differ, I don't think we can do that. Not yet. No.
Yeah. Thanks,
That's
Marina.
my view. Somebody may differ.
No, that's great. I have a couple of questions from Asan. Can installing syncons introduce new oscillatory modes?
It may, yes, yeah, because you are adding inertia. You are adding another synchronous generator, really, with P is 0. Yes, it can. But also what it can do, Asan, it can reduce your damping, because synchronous condensers haven't got stabilizers installed, so they may reduce the damping of the modes that are already there. The stabilizers work the best with the higher levels of power, and they are the least effective with low levels of power. So if you install traditional power system stabilizer on synchronous condenser, it wouldn't do anything because power is 0. So we would have to find out some other strategy how to utilize excitation of synchronous condenser to introduce damping, but not through power, through some other means. And look, that may be possible. I definitely, I haven't been involved in that, but it could be possible.
And on stabilizers again, can a reduction in inertia make the PSS less effective?
It depends how they are tuned. If they are tuned for a network at a time with high inertia, and the inertia changes a lot, oh yes, definitely, just by the nature of its tuning. If inertia reduces slightly, it may not, but yes, I would think it would definitely change the nature of damping of that stabilizer. Yeah.
And a question from Ranjith. Can you target more than one oscillatory mode through pods? Can you tune them to more than one mode?
Yes, you can. You can, but that would mean if you target one mode, then your stabilizing device is very effective. If you are targeting more than one modes, then you are spreading your force against a number of modes. So you are not achieving, you're achieving wider range of damping, but not as good range, not as good damping on any one of them. But it could be good enough. It's just that when you target, you achieve the best possible damping for that mode.
Yeah, that makes sense. Another question, what is the possibility of using EMT software such as PSCAD to understand small signal stabilities? And I guess this ties in with how we're currently looking at inverter-based resource control interactions. I guess that's mainly an EMT, isn't it, at the moment?
That's right. Yes. Yeah. Look, I think there is lots to be explored there. This oscillatory instabilities that we have here and there at higher frequencies around 20 hertz, it could well be that we'll have to study that in EMT software. But how exactly? How do you excite these modes? I am not sure. I don't think anyone is doing that yet. I haven't come across in literature anyone doing exactly that. But there could be a lot hidden in that approach, yes.
And another question, I guess, on inverter-based resources. Is there any evidence that grid-forming inverters may impact electromechanical modes?
I'm not sure. We haven't got enough experience with grid forming. Yes, look, they may because if grid forming is controlling voltage more than power to synchronize better to the network frequency and voltage, and grid forming leaves electrical power to oscillate a bit more, like what we get with non-grid forming inverters, it could happen, yes, but I'm really guessing here. It's just my intuition that's telling me that. I'm not 100%.
I don't think anyone's 100% at the moment with grid-forming inverters. Another question, are we observing the same frequency of oscillations physically in the measurements similar to the Q&I mode that is seen in studies? So I think it's saying, can we see the same oscillations in the studies that we see as measured on the system for the Q&I mode?
Yeah, that is a huge area that we really have to devote more time to, and that is the analysis of the measurements. It is not a trivial problem. It is not easy to analyze signals and find out what the damping is hidden in those signals. And we have in AEMO, we have some algorithms that were developed some years ago, maybe 15 years ago, and these algorithms are tuned to recognize certain modes and extract them via this algorithm. Now, as modes are changing, this algorithm has to be reviewed constantly to be able to state that our analysis is still correct. And it is a huge area where I think we'll have to devote more energy to. Because if we just rely on small signal software to give us the result, well, how do we know that these results are relevant? How do we know that they are accurate if we don't compare them with the measurements? And analyzing measurements and modes in measurements is not trivial.
Mm. Another question about QNI. With QNI that can have transfers limited at times due to an oscillatory stability limit, with withdrawal of synchronous generators in Queensland, can transfers be significantly clamped down further to prevent instability? If so, would an addition of an SVC with POD or PSS be an effective measure at the power station location, or Greenbank or South Pine be an effective way to reinstate transfer limits?
I think yes, yes, and yes to all these questions. I mean, this is something that I'm sure PowerLink and TransGrid are looking into, and AEMO will have to look into it as well. We do limit assessments from small signal point of view every 2 years or so, just to make sure what this displacement does to the limits. But it is an area where we have to invest and do more work. Yes, totally agree. And Greenbank and SVC may still be the best place to have pods. They may not. I don't know. Without looking into it, we just don't know.
And another more general question, are things considered differently for the distribution network, say under 22 kV in terms of
Yes,
oscillations?
yeah. They haven't got these issues at all. Issues in distribution are related to much higher frequencies, flickers, harmonics, so much higher frequencies. They haven't got these areas where you can say this part of the network oscillates against the other part of the network. These phenomena just don't exist there.
Mm. And I think this might be the last question that people have posted. Have you done any studies looking at the impact of Energy Connect or HumeLink, so those future?
Oh, I'm sure
Yeah.
there. I haven't, but I know that there are teams that are looking into
Yeah.
that. Yes, yeah, definitely. But I can't tell you. I would have to look myself to find out what the results are of those. What I know is that nobody in the NEM, not even in Tasmania, and they're usually well ahead of the game. Nobody is modeling yet asynchronous generation in small signal. Yeah, so that's coming. We are planning to attack that area next year, mid next year. We are planning to look into it and see whether to model asynchronous generation, and if yes, what is important, which frequency bands, do we just look at the bands displacement effect? So we still look at inter-area oscillations, but from the angle of displacement of synchronous generation, or do we look at high frequencies as well? But if we are looking at 20 hertz oscillations that we currently have in the system, then we have to have the model that can represent these high frequencies. And again, that's not a trivial modeling issue.
Thanks, Marina, and thanks for your very detailed and comprehensive answers to all the questions. I think that was all of the questions we had from people today. I'd like to thank you again for a great presentation. It was a very nice overview of oscillatory stability and small signal stability. So thank you very much.
Thank you. Pleasure.
All right, thanks everyone for attending.
Thank you.
And I hope everyone has a lovely afternoon.
Thank you all. Thanks for listening. Bye.
Bye.